So welcome to Arithmetic Sequence. I know that says arithmetic, but that's how it's pronounced as arithmetic. This is a sequence formed by adding the initial term A and a product of a common difference, which I'll go over in a second, D, and the term number n. So what the heck does that mean? Well, I'll go to the explicit function in a second. So let's go over the sequence. The sequence, even in the previous page here, you had a pattern of something happening to make that sequence come alive. And again, that pattern was important to establish that overall set. It's the same idea here is where we're going to have an A of n. We're going to go from A all the way to eventually n. But notice each time I'm adding a d, so other than the initialization, I'm adding one d. Now I'm adding 2Ds. Each time I'm hopping here, I'm really adding a D. That's why we have 2D, then 3D, then 4D. So it's going to be the n times the number of Ds, and again, it's the same distance in between in order to get our Frankel sequence in that overall set. Now, again, the A is the initial term here. If we had an explicit function, I want to make sure we're clear about this because this will come up a couple times. If I want a certain position, then I can use this equation. So if I wanted A of 0 or A of 10,000, I can use this equation, and that would help me find that particular location in the sequence. But the sequence is going to be all of those values that are in there, so it's going to look something very similar to this, where there's squiggly braces, which you and I are used to encoding, but that's what the set's going to have in it, squiggly braces and all the values that are in there. So let's go over an example. Very simple one. Let A equal 5 and D equal 2. So that means the distance every time from 5 is going to be 2, then 2 times 2, then 2 times 3, 2 times 4. Well, if we just look at what is called the reoccurrence. The reoccurrence, and sometimes I hear recursion and stuff like that. I know it's a dirty cuss word, but what it does is it uses the previous value to determine the next one. So if we wanted to do the first 5, we know that we're starting off at 5 because A is equal to 5, okay? Now, we could do the distance. We're not yet. We got to do the initialization first, but then we're going to add 2 to that because we know that our distance, which happens to be labeled D here, is going to be 2 times 1, so there's our 5 and 7. Then I'm going to add another 2 to make it 9, and then I'm going to add another 2 to make it 11, and then 13, and that'll be my first 5. Now again, notice I used the value before that to kind of guide me along on getting the complete set of this. Notice that also, by the way, I am using almost like an indexing system to basically describe what position each of those values are. Now, there's a big difference between this and a progression. Now this is really basically, it's also going to be called an explicit functions, or because really what I'm doing is I'm not using a previous value. All I'm doing is plugging in. There's our n of 0, 5 plus 2 of 0 equals 5. Duh, but where did I get that from? Was the explicit function. Now I put in 1. 5 plus 2 times 1 equals 7. And you'll notice I'm going all the way down here to do the exact same thing. But I didn't need a previous equation to help me figure out what it was at that current location. Notice I don't have anything about A of 2, which ends up being 9. 9 wasn't used anywhere else in this overall set to help me get to the next value, whereas in a reoccurrence, I had to use 9 to say, okay, what's 2 more than 9? That's 11. So big difference between the two of those. And remember, the two big parts that we had in arithmetic was our initialization, which was A, and our common distance. Again, the common distance in each one of these happened to be 2. I didn't really need to multiply, I just could add. Now, as you know, if you do the same thing over and over again, it is multiplication. That's why we can get away with this. But anyway, for example number 2, we're going to try to find A and D for a sequence that's already basically given. For this one, which is funny, we're actually going to use subtraction to identify the closed equation that you and I are really looking for, which eventually will end up being this. But how do we do that? A is 7, which is already given. Notice we already were given 7 in the original set. That's our initialization point or starting point. A is given. But how did I figure out D? D was actually solving using the difference between each of those values. So I just happened to pick the first one here. 4 and then minus 7 is a negative 3. Now I could have done it 1 and 4 still would have been negative 3. Notice that that's their common distance between each of those, so that's why I can get away with that and saying that negative 3 for all of those. So if I'm given the common distance for all of this, I can end up having my equation being, well, frankly, this. So that it should work out for the set that we've got right here. So try for a of 1. Okay, well, if a at 1 is going to be 7 plus negative 3 times 1, which is still going to be negative 3, that equals our 4. I bet if I did it for 2, and then for 3, it's going to match up. But that's how we get our equation where it's arithmetic and, frankly, being able to fit and make it easier on us in the long run. Now, be careful, by the way. It's got to fit this overall sequence or explicit function. Notice there's a plus in the overall form. We're going to watch that a little bit later on, hoping that it matches some other things that we have coming down the road. So just watch out for that pattern.